Hi, everyone. So we are at the last day of our fourth week of lectures. Today is 4.6, limits at infinity and asymptotes. So we will be talking about limits at infinity and asymptotes, obviously, since that's the name of the section. And then we'll kind of wrap it up by talking about how to graph um, a function, specifically a polynomial function, kind of based on what we were doing the past couple of days and using a little bit about what we know today. All right, so the first couple of slides, um, I may encourage you not to write anything down. There's going to be quite a few slides where um, it's kind of redundant. So we're going to give you some informal definitions first, and we'll give you the formal definitions after. But it's really going to be about you understanding it conceptually before anything else. So here is just an idea for your understanding. So the limit as x approaches a of f of x equals L means that f of x becomes arbitrarily close to L. So as we can see, as we get closer and closer to this line right here, the function tends to go towards that line as we get to whatever value we're looking at. Usually it's going to be either positive or negative infinity, as it says down here. All right, so this is something that we're going to have to keep in mind throughout the lecture today. So this is something that I may say, let's not write down right this second. This is the informal definition. If you'd like to write this down, you can right here. So we have this concept of a limit at infinity, or a limit to infinity. So this is the limit as x approaches infinity of some function, and we're saying that it is a number, where L is some number. So we could have it be a value here, or we may not have it actually be a value. So this is a positive infinity, but we also really want to consider what happens at negative infinity as well, because we don't just want to look at one side of the function, we want to look at the entire function in general. And so we also want to look at negative infinity. It's a little bit hard to see that here, but this is a negative infinity down here. So the limit as f of x approaches, the limit as x approaches negative infinity of f of x is also going to be L. So you notice in this case, it'll be the same limit. And we'll do some examples with this. So this is a formal definition of a horizontal asymptote. So if you've taken pre-calc, you may recognize that terminology of horizontal asymptote. And in fact, you may remember some ways to actually compute the horizontal asymptote of a rational function, given that a rational function is a polynomial over a polynomial. So if you remember those tricks, you can, of course, use that given a homework question to check your work, but I encourage you to do it the way that we're doing it now, kind of the more calculus way of doing it, just to make sure that you're understanding all of the different aspects of computing the horizontal asymptote. So a horizontal asymptote here could have different values theoretically. So if the limit as x approaches infinity of f of x is L, or even negative infinity, then y equals L is the horizontal asymptote. That's just what it means to be a horizontal asymptote. And we remember that we can never cross a vertical asymptote, but we can cross a horizontal asymptote. The only restriction is that we have to tend towards the horizontal asymptote kind of in general. So even if we peak above it, we have to go down and dip back towards it and stay going towards it for infinity. All right, so let's just do a quick example. For each of the following functions, well, we just have one. Evaluate the limit as x approaches infinity of f of x and limit as x approaches negative infinity of f of x. All right, so what we have to consider when we're looking at functions is the positive versus the negative infinity and how that plays a role in the function. So first we'll look at positive infinity because typically we don't have to do anything too crazy when we're looking at that. So we'll look at the limit as x approaches positive infinity of 5 minus 2 over x squared. And what we can remember from, I think it was section 2.3, our limit laws, is that if you have subtraction and you're looking at a limit, you can actually break it up into two limits. So you could actually look at this as a limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared. And this helps us a little bit because the limit of a constant, this was also a limit law. If you just have a constant, as you go towards infinity, your constant's not going to change. So this is just going to be 5. Now, this, on the other hand, is going to be something that we'll compute. So if you think about plugging in the idea of infinity, now you can't actually plug in infinity, but we like to think about plugging in infinity or at least a very, very, very large number, and that kind of gets us to where we need to go. So if you think about putting the largest number that you can consider in the denominator of a function where the numerator is just a constant, take that divided by the largest number, you're going to have the largest decimal that you could possibly imagine. And in fact, that decimal will be almost zero. And so anytime you have a very, very large number, you have like 2 over x as x approaches infinity or x squared or anything kind of that sort, your answer is going to be 0. The limit will tend towards 0. And so you have 5 minus 0. And so your answer is going to be 5. Now, we also will have to consider the limit as x approaches negative infinity, since that's part of the question. And we have to consider what might change in the function if we're looking at negative infinity as opposed to positive infinity. So we have the same construction, except that we have it with a negative infinity instead. So we could, of course, break it up the same way as we did before. Negative infinity of 5 minus the limit as x approaches negative infinity of 2 over x squared. And this doesn't change. The limit as x approaches 5 or as x approaches negative infinity of 5 doesn't change because it's still a constant. So as far left as you can imagine is the same thing as far right as you can imagine. So it's still just going to be 5 because that's the constant law. Now, this is where we have to consider what's happening. And specifically, we have to consider the exponents. If you take a negative number, and I know that it's negative infinity here, so just kind of bear with me about the fact that this does in fact work. If you think about any negative number, and you square that negative number, you wind up with a positive number. So if you plug in negative infinity, well, that's about the same thing as plugging in positive infinity. In fact, it's the same thing as plugging in positive infinity. So you do 2 over positive infinity, you get 0. And so your answer is 5. So in fact, the limit going to infinity and negative infinity is going to be the same answer in this case because the value that we are plugging this infinity into is a squared value. It will change if you have, say, cubed, right? If this was a cubed function instead of a squared function, well, if you cube any negative number, it stays negative. And so in that case, you would have to bring the negative along with you. Now, again, this would still just be 0 because negative 0 is 0. But if this was a value, you would have to bring the negative along with you. So that's something that we're going to have to keep in mind. All right, so this is just another informal definition. So we say that f has an infinite limit at infinity. So this is a little bit different than the first one that was just a limit at infinity. This is an infinite limit at infinity. And we can write that a limit is equal to infinity, like this and like this. It could be positive or negative infinity. There are some disputes in the world of mathematics whether or not we can write this because some people argue that limits have to be equal to a number and infinity isn't a number. So therefore we can't have it and we should say that the limit doesn't exist. But then the other hand, we say, well, we do know where it's going. We know it's going to positive infinity. It's not like it's going to negative infinity, and there's a big distinction there. So we should at least indicate that distinction. So it's just a really big debate. There's no right answer. I fall on the side of if it's positive infinity, just write it. Let's not say it doesn't exist. While it's not a number, there is still some concept that it's going towards. It's not a number, but it's a concept. So that's where I lean. But that's this informal definition. So now we can actually get to the formal definition. So right off the bat, we're going to look at this and we're going to see something weird. We're going to see this right here. That's called an epsilon, for those of you familiar with Greek letters. So I'm going to put it out there. I am not going to be testing you or giving you any questions or anything like that on the formal definition of a limit. Okay, so before you get nervous about having to remember all of these weird definitions, I don't expect to see this. This is just something that you should be exposed to at some point. Now, if you do take any further math courses, if you get into any sort of analysis courses or anything like that, you are going to see stuff like this. So it's important to kind of have a grasp of like, oh, okay, I've seen this before and I understand the concept. So what this says is for all epsilon greater than 0. Typically, when we say for all epsilon greater than 0, we're considering a very, very small epsilon, the smallest number that you can imagine. there exists an n greater than 0, whatever n that you can think of, such that, and typically, again, these are pretty small numbers, f of x minus L, so your function minus your limit, is less than epsilon. Um, we will usually also want to look at the limit of this thing, as you can see right here. So the limit of your function should be L. So the function, as you get closer and closer to infinity, should be equal to the limit. So when you subtract them, they should be almost 0. That's why we want to consider a very small epsilon. So your epsilon can vary. That's why we just say it's greater than 0. It's not going to be equal to 0, but it's going to be the smallest number that you could possibly imagine. So it says if this and this is true, then your limit exists. So this is the official formal definition of a limit at infinity. You can also find very similar definitions using epsilons and deltas for continuity and for similar things. I believe that there are some in the textbook if you're curious and you're planning on going into further math courses and you want to check it out. You can also ask me and I can direct you to some of those resources too. All right, this is the same idea. Again, don't think that you have to know this. This is just kind of for your understanding. This is the formal definition of an infinite limit at infinity. So you can have the same idea, but now our limit isn't a number, it's infinity. So instead of having an epsilon greater than 0, because epsilon is typically a very small number, we're just going to say we have an m greater than 0 because we don't know what m is. And then there exists an n greater than 0 such that your function is going to be bigger than some m value. And so you can read this, digest exactly what this is saying. But the informal definitions are going to be more so what we're going to be using throughout this lecture and the rest of the course. All right, now we get to this idea of end behavior. Again, if you've taken a pre-calculus course or you remember any of this from like an algebra 2 class in high school, this should be very familiar. I know at least in New York State's algebra 2, of course, I don't know where you're taking this class from or where you went to high school, but in New York State's algebra 2 curriculum, you definitely talk about end behavior, you talk about graphing functions, or at least you should talk about that because that's in the standards. So let's understand the idea of what end behavior is. So the limit as x goes to positive or negative infinity is going to be your function's end behavior. So whatever is happening there is the end behavior of the function, which feels pretty natural, right? Whatever's happening at the end is the behavior of the function. That feels pretty intuitive. Um, so there's kind of a couple different situations. So there's three situations that we may have. The first is that we have a very nice horizontal asymptote, right? We've got some line, and then because we have a horizontal asymptote, both of the functions ends will go towards the horizontal asymptote, and it'll look very pretty, very nice. So that's this first case, right here. Now, the second case, if you think of like a cubic polynomial, for example, that kind of goes from down to up, we're going to have something going to negative infinity and something going to positive infinity. And that's the end behavior, the negative infinity and the positive infinity. So you may have a function where the end behavior is just some form of infinity. Now, you may also have a function where you don't have any solid end behavior. And I definitely encourage you to take a second before I tell you an example, to think of an example yourself of where you might not have end behavior. So if you want to pause the lecture and just kind of think about that for a second, go ahead. But I am going to give you the answer because I don't want to leave you on a cliffhanger. So an example of somewhere where you would not see any end behavior is something like a sine or a cosine function, right? If you think about sine kind of just starts like this and it goes on forever and ever and ever. And then it also goes on forever and ever in the opposite direction. So as you look at the limit as x approaches infinity, there's never going to be a limit because no matter what part you're looking at, it's going to be changing forever. It's not going to approach anything in particular. So sine, cosine, and there are several other examples of especially things to do with trig that oscillate. All right, and these are some examples. So here's some end behavior. This is like any kind of an even polynomial, where n is a positive integer. So this is an even polynomial. This is x squared, x to the fourth, x to the sixth. The n behavior is going to go to positive infinity. So I don't know if that says this. So n here is even. Over here, as you can see, you have n behavior in different directions. So when you have n behavior in different directions, that indicates that your function is an odd degree function. So here, this is odd. Don't get that confused with being an odd function or an even function. We have an even and odd degree, not necessarily telling us if the function itself is even or odd. That has a different definition. But these are all odd degrees, as you can see. So the n behavior will be different. So that's just something to keep in mind. So let's go ahead and just briefly evaluate the limits. You don't have to memorize anything in this case. It's actually as simple as kind of plugging in infinity. I don't necessarily like saying that because you can't plug in infinity. You can only plug in numbers, but that's essentially the idea behind it. So if you look at A, and you're looking at f of x equals negative 5x cubed, and we're looking at the limit as x approaches infinity of negative 5x cubed. If you consider plugging infinity into this x right here, well, anything times infinity is infinity, right? And infinity cubed is also infinity. Therefore, we just have to consider the sign of what the infinity will be. Since this is positive infinity cubed, this will be a positive infinity. But because we have a negative infinity or a negative 5 here, we have to multiply the infinity by a negative value. So that will be a negative infinity limit as x approaches positive infinity. Now, if we consider the limit as x approaches negative infinity of negative 5x cubed, we again can first think about like plugging in negative infinity into your x cubed. Because negative cubed is negative, you would get a negative infinity out of that. But when you multiply negative infinity by a negative, you get a positive. And so we're just going to keep the infinity. There's nothing that would get rid of the infinity, so we're just going to keep the infinity, but we do have to deal with the sign. For b, we want to do the same thing. So the limit as x approaches positive infinity of 2x to the fourth. Well, if we think about kind of plugging in infinity, infinity to the fourth is still going to be infinity. Multiplying it by 2 doesn't matter. So that's still going to be infinity. If we now consider the limit as x approaches negative infinity of 2x to the fourth, well, if you take a negative number and you raise it to the fourth power, that makes it positive. And then if you take a positive number and you multiply it by a positive number, that's also positive. Therefore, infinity to the fourth is just infinity, and your answer is just infinity. So this is just going to be a good example of seeing the differences between what will happen depending on the degree of the polynomial or power function that you're looking at. And this is kind of what's going to happen if your rational function is not a simple one term over a one term situation. So again, I mentioned that some of you may have taken pre-calculus and you remember the rules. If you have the same degree, then your horizontal asymptote is the ratio of the coefficient. If you have a lower degree over a higher degree, then your horizontal asymptote is 0. And if you have a higher degree over a lower degree, then you don't have a horizontal asymptote and your limit will be some infinity. We're not going to use those now. We're going to use our calculus techniques to find the answer. So let's go ahead and take a look at this. So we want to look at limits at infinity of rational functions of this form. And we're going to consider the degrees of the numerator and the denominator. So in particular, we divide the numerator and denominator by the highest power of x appearing in the denominator. So that's very, very important. So we'll take a look at the denominator, find what the highest power is, and we're going to divide by that highest power. We're then going to try to evaluate that function and see what happens. Your answer may still be infinity, but you may actually also have an answer. So this is going to be the algebraic way of solving these functions. All right, so let's go ahead and take a look at these three cases. So like I just explained to you, we remember the three rules from pre-calculus. These are an example of each of the three rules. So right off the bat, I can tell you that A should approach 3 over 2, B should approach 0, and C should approach either infinity, depending on where we're going. And I know that based on my pre-calculus rules. Now let's use our calculus techniques to show this. All right. So here's a. F of x is 3x minus 1 over 2x plus 5. This is a graph of a. You're not going to be given a graph if you're given something like this on, say, a written assessment or an exam or a homework. But this helps us to see that we will, in fact, have exactly what I mentioned, which is a horizontal asymptote at 3/2. So the rule says we want to divide by the highest degree in our denominator. So first we'll look at, oops, I keep telling you that I might get better by the end of the semester about remembering to switch my pen, but you know, it's week 4, the end of week 4, and I'm not yet. So maybe I'm just not going to do that. Maybe I'm just going to be bad with this semester. The limit as x approaches infinity, we'll do infinity and we'll look at negative infinity as well. Limit as x approaches positive infinity of 3x minus 1 over 2x plus 5. So what we want to do is divide every single term by the highest degree in the denominator. This is a single x. We only have one variable, so we have to divide everything by x. And so this is equal to the limit as x approaches infinity. And then we're going to divide every term individually by that term, because what you do to one thing, you have to do to everything. So this is 3x over x minus 1 over x over 2x over x plus 5 over x. And again, I'm dividing that because that's the highest degree variable in our denominator. And then I'm going to simplify this. I don't want to do anything with this yet. So we're going to have the limit as x approaches infinity. 3x divided by x is just 3 minus 1 over x over, we see here this turns into 2 plus 5 over x. Because if you notice here, you try plugging in infinity, well, you get 3 times infinity over 2 times infinity, and you're adding and subtracting a little bit, but you're not actually getting an answer. With this method, you will actually get an answer. Because now, once we go ahead and kind of alter the way that our equation looks, we can go ahead and plug in our limit. We could apply our limit to this function and see what happens. We know that the limit as x approaches infinity of a constant over infinity is going to be an infinitely small number that is pretty much just 0. And so what this turns into is actually going to be this goes to 0 and this goes to 0 when you apply the limit. And so this limit is, well, this constant stays the same and this constant stays the same. So your limit is just going to be 3/2. Now, you notice that if we applied negative infinity, nothing would change, right? So if we did the limit as x approaches negative infinity, all of the algebra stays the same. You don't change any of the algebra. So I'm just going to jump right to this step because we've already done the algebra. No point in doing it again. Over 2 plus 5 over x. Now you plug in negative infinity. Well, 1 over negative infinity is also pretty much just 0, except it's negative 0.000, but now put in infinitely many zeros and like a 1 at the end. That's pretty much still just 0. It doesn't matter if it's positive or negative. It's essentially 0. And so this still just becomes 0, and this still just becomes 0. And so this becomes 3/2. So you notice that these two answers will be the same here. All right. And this confirms that our technique does work. This is the algebra that you would be expected to show, though. Let's go ahead and try another example. So here we have another rational function, except that we have a lower degree in the numerator than we do in the denominator. And this is what the function looks like. So it's kind of funky looking. And I don't think that you would necessarily expect that this is what your function would look like if you just saw this. So let's consider positive infinity first of this function. So 3x squared plus 2x over 4x cubed minus 5x plus 7. All right, again, you can try to plug in positive infinity. The first step is always going to be try to plug it in. Maybe I haven't done that so much because it's just assumed that it's not going to work. Like 9 times out of 10, if I give you a question, it's not going to work. You're not going to be able to do anything. You have to do something else to it. I usually forfeit the step of like actually trying to plug it in because again, you try to plug this in, you get infinity over infinity, you get an indeterminate form, you have to do something else with it. So let's go ahead and use our rule to actually figure out what this limit could be. So the rule says you want to divide everything by the highest degree in the denominator. As we see, that's going to be this x cubed. Be careful to check every term because it may not necessarily always be written in the standard form, which is like highest degree, next highest degree, next highest degree down to the constant. It could be written in a funky way. All right. So I'll divide everything by just x cubed. I don't necessarily want to keep the number out front and divide that. I mean, you can, it doesn't change anything, but it's easier just to divide the variable. So this turns into the limit as x approaches infinity. of 3x squared over x cubed plus 2x over x cubed all over 4x cubed over x cubed minus 5x over x cubed plus 7 over x cubed. Now we'll simplify. Limit as x approaches infinity of the x squared and the x cubed will divide to be 3 over x. So this is where it's very important that we remember all of our rules of exponents. 2x over x cubed will turn into plus 2 over x squared over. The x cubes will cancel out here, so it's just 4 minus the x and the x cubed will turn into 5 over x squared. And then this you can't do anything with, so it's just 7 over x cubed. Now we can go ahead and actually plug in the limit. So again, we know that if you have a constant over an infinity, that just turns into 0. So you get 0, 0, 0, 0. So this turns into 0 over 4, which is just 0. So your limit is going to be 0. As you can see, this tends to 0 here. We can also consider the limit as x approaches negative infinity. And again, if you just want to look at here, because you don't need to do all the work again, it's the same exact work. If you take this and you consider the limit as x approaches negative infinity of our function, I'm not going to rewrite it because it's right here. Plugging in negative infinity here again doesn't change anything because you're just getting a negative infinitely many zeros and then a 1 that is like identically 0. So this is 0, this will be 0, 0, 0 over a 4. So this still is 0 over 4, which is going to be a 0. So these are the two limits. And when you're talking about the end behavior, this is the end behavior of your function, is exactly what's happening here. All right, let's take a look at this last example. As we see, it has this kind of funky looking shape. This actually has something called an oblique asymptote. So oblique just kind of means like tilted, slanted. It's also called like a slanted asymptote. So instead of a horizontal or a vertical asymptote, because it does have a vertical asymptote at x equals -2. I believe it also has an oblique asymptote. I will not be testing you on that though. So let's go ahead and take a look at the limit as x approaches infinity of 3x squared plus 4x over x plus 2. And we will once again be dividing by the highest degree in our denominator, so that'll be just a single x. So this is the limit as x approaches infinity of 3x squared over x plus 4x over x over x over x plus 2 over x. Divided everything by x, and then I'm going to simplify. Keep my limit. 3x squared over x is going to give me 3x. Here my x's cancel out, so this is plus 4 over here. This becomes 1, and then this stays as plus 2 over x. So now when I go ahead and plug in infinity, I notice that this goes to 0. So I do have a denominator of 1, but up here when I plug in infinity, I get infinity. And so my answer for this is actually going to be positive infinity. As you can see, this is the case when we look at the graph. Now, if we consider the limit as x approaches negative infinity, again, we'll go from this, we'll go 3x plus 4 over 1 plus 2 over x. Now the infinity sign does matter. When you're dividing by it, sometimes it doesn't necessarily matter if it's just a single variable in the denominator and you have a constant in the numerator. But when you have a variable not in a denominator, it does matter. Because again, you plug in negative infinity down here, the 2 over x does go to 0. So this is 1 plus 0, which is 1. But when you do 3 times negative infinity, you get negative infinity. Negative infinity plus 4 is still negative infinity. And so your answer for this one is negative infinity, where you do see that that's the case again as x approaches negative infinity this way, y goes down as far as you can think, which is negative infinity. So we've again confirmed that this does not have any horizontal asymptote. All right, here's another example, but it's a little bit weird this time. So now it says we're looking to find the limits, right? The same thing we've been doing, but now instead of our typical rational function that we've been working with, we have a square root. So when we're considering a square root function, what we want to do more or less, we're going to kind of play with things a little bit differently than we would. So we're going to consider the variable to be the highest degree under the square root, but then we have to consider the fact that it is a square root. We are going to pretend the 5 isn't there or whatever else isn't there when it comes to just considering the highest degree. So what I mean is the highest degree in the denominator is not a square because you have a square root. So I want to get rid of anything arbitrary, anything that just does not matter, which means the 4 doesn't matter and the plus 5 doesn't matter. What matters is that we have an x squared and we have a square root. So in our denominator, we have the square root of x squared, which tells us that the highest degree in the denominator is x. And the reason why we need to know that is because in the numerator, we do have an x. In the denominator, we have a square root. So we're going to take both of those things into consideration. And I'm going to show you exactly what I mean. So let's look at the limit as x approaches infinity of this function. 3x minus 2 over the square root of 4x plus 5. So this works a little bit different than you would expect it to. So you still want to divide by the highest degree in your denominator, which we determined was x. So the numerator, you'll be dividing by x. It's just what you would expect. So 3x over x minus 2 over x, nothing different there. But your denominator things do change because why would you divide x with a square root? You wouldn't. So you want to consider the fact that we're still, oh, I forgot a square there, didn't I? That you still have a square root. So what you'll do is I'm going to put a big square root. I need to take each of these two terms here. And instead of dividing by x, what I'm going to divide by is the square root of x squared. Because as we just showed, this is the same thing. But because we put a square root in here, we can move it inside of our root. And so this is what I mean. We have 4x squared. We'll put a fraction bar plus 5 over. And now we need to decide what to put in our denominators. Because we know that x is equal to the square root of x squared, and this is all under the square root, I can write in x squared because we have a rule that says that we can separate out our root by numerator and denominator. If you need a little bit of a refresher on root rules, exponent rules, I'd be more than happy to help you out and give you that refresher. So we're actually going to be dividing by the x squared under the square root because it's the same thing as x. So now we're going to adjust this, and I forgot to write the limit in. Don't forget that. So this is the limit as x approaches infinity, and we're going to actually kind of simplify. We're going to simplify the numerator and the denominator. So this just becomes 3 minus 2 over x over. So we're going to keep the square root here. This just becomes 4 plus 5 over x squared. Again, this is all under the square root. And now we can plug in the infinity. So you plug in infinity into this, it goes to 0. You plug in infinity here, it goes to 0. So what you wind up with is 3 over the square root of 4, but the square root of 4 is just 2. So you get 3 over 2. We'll do the same exact thing with negative infinity. The limit as x approaches negative infinity, and I'm going to start here again. 3 minus 2 over x over the big square root of 4 plus 5 over x squared. When you plug in negative infinity, this still goes to 0, and this still goes to 0. These don't change at all, no matter which infinity you look at, because you're not plugging anything into those. So you still get 3 over the square root of 4, which we just determined was 3 over 2. So that's the end behavior of f. As x approaches infinity and negative infinity, we approach 3/2. Now, what about if we don't have a regular type of a rational function? What about if we have an e? Well, this we actually have to consider slightly differently. So this is the harder example of the functions. So we're going to do it in the same general way that we have before, but now we have to consider a few extra rules. So we'll look at the limit as x approaches infinity of our function first, as always. Oh, why did I write? See, I'm writing new things. 3e to the x over 7 minus 5e to the x. All right, so this is our function. And we still have to consider what the highest, I don't even want to use the word degree, but the highest variable thing in our denominator is. And in this case, it's just going to be e to the x. So it's going to be the thing with the fastest growth rate, essentially. So even if I had added like plus x squared, plus x cubed, plus x to the fifth, e to the x will grow faster than those functions. So there's a difference between power functions and exponential functions, and exponential functions will grow faster than power functions will. So anytime you have an e to the x, that's going to be your highest degree. If degree in quotes. Again, it's not actually a degree. I feel like this whole lecture is very much so. Think about it like this, but it's not totally that. Like that's just kind of the gist of this lecture. So we're still going to be dividing by e to the x. So anytime there's an e to the x in there, that's what we're going to be dividing by. Even if, again, there's a bunch of like x's and stuff like that, that's going to be the most important thing. That's going to be the thing that grows the largest, the fastest, going towards the end. So let's divide everything by e to the x. So we get the limit as x approaches infinity of 2 over e to the x plus 3e to the x over e to the x over 7 over e to the x minus 5e to the x over e to the x. And we can simplify this to be the limit as x approaches infinity of 2 over e to the x plus 3 over 7 over e to the x minus 5. Okay, so now we simplified this a little bit. Again, if you try plugging infinity in here, and e to the infinity is infinity, anything times plus infinity is infinity, so you don't actually get anything helpful if you were to just try plugging it in right from the start. So we need to do this. Now that we've adjusted it, we can actually try plugging in a value. If you plug infinity into this function, e, you have to remember, is a number. It's similar to pi. E is approximately 2.717, and it goes on forever and ever. So if you consider taking some number, you can even think about 3 if you'd rather. 3 is a nicer number. If you think about 3 to the x, well, 3 to the infinity is an infinitely large number. If you do 2 divided by infinity, I don't know why I said it like that. 2 divided by infinity, you get 0, right? 2 divided by infinity is 0. You get like infinitely many zeros. 1. Pretty much 0. So this thing goes to 0, which means that this thing goes to 0, which means that what you're left with is just 3 over minus 5. So 3 over negative 5. So this is the limit as x approaches infinity. Now we also need to consider the limit as x approaches negative infinity. So far, we haven't seen a case where the number that we've gotten is actually different. But now that we're not looking at the typical rational function, we're looking at e, we can actually have a difference. So again, we're going to start with this right here. We're going to have 2 over e to the x plus 3 over 7 over e to the x minus 5. Now, if we try to plug in negative infinity, well, e to the negative infinity is a different number than we would expect. So we have to remember this rule of having a negative exponent. If you have e to the negative infinity, what that means, or like 1 over e to the negative infinity, let's say, because this is in the denominator, is if you want to get rid of the negative, you have to move the place that that function is in the fraction. So if you have it in the denominator, you want to make the exponent positive, you bring it into the numerator. And so this actually becomes e to the positive infinity. But that becomes an issue. So let's go ahead and take a look at this. So if we try plugging in negative infinity, we get 2e to the infinity and 7e to the infinity, which could become an issue. So instead, maybe we consider doing it a slightly different way. First, might I suggest, from the beginning, let's see here, what would the easiest way be? So I might suggest that we can alter this expression in a way that makes a little bit more sense. So instead of looking as x approaches negative infinity, we can look about x approaching positive infinity, but then adjust the function itself. So let me go ahead and do that. I'm going to erase this, and we're going to kind of do it from the beginning and show that the answer is actually different than what we would expect. So if we have 2 plus e to the x, 3e to the x over 7 minus 5e to the x. And we're looking at x approaching negative infinity. We can also consider that maybe x would approach positive infinity. But if x approached positive infinity, then in order for this to be the same, we would need to negate the x value. So 2 plus 3e to the minus x over 7 minus 5e to the minus x, right? So if you plug in positive infinity, this is now negative infinity up here, which is the same thing as having a positive x and plugging in negative infinity there. Because otherwise it might be a little bit tricky. You'd have to do a little bit more algebra to get there. So maybe in a situation like this, you just want to start over. All right, so again, what we did was we saw that we were going to negative infinity. We knew that it'd be a little bit trickier, so we're adjusting the function itself. So instead of saying x is going to negative infinity and keeping positive x's, we're saying, okay, maybe x is going to positive infinity and we're going to negate our x's. Same answer, different way of getting there. Now we can follow the same steps, divide everything by negative infinity. So we get 2 over e to the minus x plus 3e to the minus x over e to the minus x, all divided by 7 over e to the minus x minus 5e to the minus x over e to the minus x. And this is the limit as x approaches positive infinity now, which will give us the limit as x approaches infinity of 2 over e to the negative x plus 3 over 7 over e to the minus x minus 5. But we still run into a slight issue here, right? So we try to plug in positive infinity, but we need to adjust this again. So maybe instead of dividing by negative infinity, let's see, we can adjust this function again. So what I'm thinking, so this is kind of my reasoning for what I'm thinking. If you plug in any form of infinity, right, this is going to be a small number here. So that doesn't actually help us. This, if you plug in infinity, becomes a very tiny number, which makes this whole thing become a large number. So this whole thing goes to infinity over infinity, and it actually doesn't help us. What we need is for something to be 3 divided by e to the positive x, very similar. I can move my face, very similar to what we had here. So in fact, what I'm going to do is I'm going to adjust this one more time, and I'm going to say, okay, this is maybe still the limit as x approaches positive infinity, but now I'm going to multiply both sides by e to the negative x, because then that gets rid of these e to the negative x's. So this can be 2 plus 3. Oh, I say 3 and I write e. It'll be 2 plus 3e to the negative x. I'll erase this. I'll rewrite it properly for you. 3e to the negative x over 7 minus 5e to the negative x. And again, I just did that by multiplying everything by e to the negative x. And what that gives us is now we can use this rule that I mentioned up here, that if you have a negative exponent, you can change the part of the fraction it's in and change the sign of the exponent. And we can rewrite this as the limit as x approaches positive infinity of 2 plus 3 over e to the positive x over 7 minus 5 over e to the positive x. Now we're in business, because now if you plug in positive infinity, e to the positive infinity becomes a very, very large number. When you do a number divided by a large number, you get 0. So this goes to 0, this goes to 0, and your answer is just going to be 2 over 7. So we notice that the limit as x approaches negative infinity of this type of a question is actually going to be a little bit more difficult than we anticipated, but it's actually totally doable as long as we manipulate the equation in a way that will work for us. All right, so this is the last idea. What we're going to do today, it's going to be sketching a graph. So this is something that we've kind of hinted at for the past 2 lectures, talking about maxima, minima, and then we did intervals of increasing and decreasing and concavity and inflection points, and all of that comes into play when we're talking about actually graphing something. So we're going to take a look at what the steps we need to take are to graph a function. So step one, in order to graph a function, is going to be we need to determine the domain, x-intercepts, and y-intercepts of the function. Typically, your domain will probably just be everything. There could be some cases where you have some sort of a maybe vertical asymptote that you have to take into account, but at least in this course, I will probably give you polynomials where the domain is just everything, so you don't have to worry about it. So the main things are find the x-intercepts and find the y-intercept of the function. Step two is going to be finding the critical points. And we remember that is when the first derivative is equal to 0. And then we want to solve to find the x values. Once we do that, we can determine the intervals of increasing and decreasing using a number line. Step three is find the second derivative. Again, set it equal to 0, solve for x. And then we can use that to determine the intervals of concave up, down. And then we can also find the inflection point based on if there's a change in concavity. Once you find all of that information, my suggestion, this is just my suggestion, is to write all of your intervals on the bottom of your set of axes and then plot your x and y intercepts and then sketch the graph. So I'm going to go ahead and show you exactly what I mean by that. So this question says sketch a graph of the polynomial f of x equals x minus 1 squared times x plus 2. So let's just go ahead and find all of our information. So first, the y-intercept is probably the easiest one that we can find. That's just f at 0, which is negative 1 squared times 2, which is just going to be 2. The x-intercepts here are also pretty easy because it's already in factored form. So you're just going to set this thing equal to 0 and solve, which again is pretty easy. You're just going to set each term equal to 0 and solve. So you actually get that x equals 1 and x equals negative 2. All right, not so bad so far. Now we're going to want to start with the first derivative. So f prime of x equals, well, the issue with this is that it is in a factored form. So the first thing that we're actually going to have to do is determine what it is either in distributed form, or we're going to have to figure out the derivative using the product rule. Let's go ahead and try the product rule out. So the product rule says first times the derivative of the second. So the first is just x minus 1 squared times the derivative of x plus 2 is just 1, so I don't need to write that, plus second, which is x plus 2, times the derivative of the first. So that'll be a chain rule. So that's x plus 2 times the derivative of the first is going to be 2, x minus 1, times the derivative of x minus 1, which is 1. So we can go ahead and solve this out right here. Let's see here. Is there any nice way of doing that? Let me check to see if there's a nice way of doing that. So if we do distribute and refactor, I'm just going to give you that the answer to this is going to be 3 times x minus 1 times x plus 1. So if you're looking to solve this, you're going to want to set this equal to 0. And what you get is that x is 1 and x is negative 1 are going to be your critical points or critical values, whichever kind of terminology you'd rather consider. So now we can go ahead and create our number lines to determine our intervals of increasing and decreasing. So this is f prime of x. And we can say here's negative 1, here's 1, and we can test points within our intervals. So I'm not going to write out every single interval. I'm just going to explain to you how I do it. So first, let's choose a number less than negative 1. Let's say negative 2. I'm going to go ahead and plug it into my factored form with the first derivative. It'll make it a little bit easier for us. So negative 2. 3 is a positive number, negative 2 minus 1 is a negative number, negative 2 plus 1 is a negative number, negative times negative is positive, positive times positive is positive. Therefore, this is all positive. All right, if I kind of spit that at you and you want to slow down, plug in negative 2 and confirm that you will get some positive value. All right, here we'll plug in 0. That's probably the easiest number. 0 minus 1 is negative, 0 plus 1 is positive. So this is just going to be positive, so we don't really need to worry about that. So negative times positive is going to be negative. Last one, we could plug in 2. 2 minus 1 is positive. 2 plus 1 is positive. Positive times positive is positive. So this tells us that we're increasing up until negative 1. We're decreasing between negative 1 and 1, and we're increasing from 1 on. Now we can discuss the second derivative. I can also mention the maximums and minimums. We should note them. You could be asked to find them. In the case of sketching it, you don't have to note that this is a max versus a min. It should just come naturally when you graph it. But going from increasing to decreasing is a max, and decreasing to increasing is a min. So if you're actually explicitly asked to find it, you can go ahead and find it based on the sign analysis. But also, like I said, it should just come when you're actually graphing it. If you go from increasing to decreasing, the turning point that you create is naturally a maximum. All right, the second derivative is going to be the derivative of this guy, and I will just tell you it is 6x. And if you set that equal to solve, you set that equal to 0 and solve, you get that x is equal to 0. So we again want to create a number line, test some points. This is the second derivative. This one's even easier. Plug in -1, negative times positive is negative. You plug in +1, positive times positive is positive. That was probably the easiest plugin you'll ever have. So what this tells us, the second derivative is concavity. So this is concave down, and plus tells us concave up. Because we do switch concavity at 0, this is an inflection point. So you will see the change in concavity on your graph. All right, so let's see. We've created our intercepts. We've found the critical points. We found the concavity. Let's go ahead and create our axes. So I'm going to get my axes up and apologize in advance because drawing, again, is not my strong suit. I stopped taking art class in like 9th grade and I never looked back. Okay, so this is what I mean when I say create intervals on the bottom of your axes. So first of all, I'll go ahead and create some tick marks and plot my points so that we kind of have a frame of reference. So I know that our x values, as we see here, are 1 and -2. So I'll go like 1, 2, 3, 1, 2, 3, -1, -2, -3. And then we see that we have a y-intercept of 2. And this is the only place where y is going to come into play. We don't care about the y value besides that. 1, 2. Okay, so here's our y-intercept. Our x-intercepts are here and here. All right. Now we're going to go ahead and just write in what's happening. First, we're going to start with our first derivative. So this is what it looks like. If we see we're increasing until -1, I'm going to put a little line here. And I'm going to draw an arrow this way, and I'm going to write we're increasing. I see we're decreasing from -1 to 1, so I'm going to go from -1 to 1. We're decreasing. I see that I'm increasing from 1 on, so from 1 forever, we are increasing. So now when we're sketching it, we don't have to keep referencing back to our anything at all. We can just look directly below our axes and see exactly what we're doing. Now we're going to overlay our concavity so that we can see when we're increasing concave up, increasing concave down, and so on. All right, we see that we are concave down until 0. So here's 0. All the way out here, we're concave down. And I do typically draw my arrows to about the same point just to know when I'm actually drawing the graph itself to see exactly what's what. And then it says from 0 on, we're concave up. So from here, forever, we're concave up. All right, now that we know all of this information, we can go ahead and actually plot. So while we don't necessarily have end behavior here, we can infer what our end behavior will be. If I know that I have to touch this point and we're increasing concave down, if I'm increasing in this quadrant, I don't ever touch that intercept. So I know I have to start down here. And we're concave down, and I remember that up looks like the smiley face, down looks like the frowny face. So if we're increasing concave down, we're going to look something like this. So I'm going to go like this, touch that point, put an arrow here, and then I'm going to see what happens at this point. I see that I'm still increasing, which means that I have to pass through this, and I, in fact, increase until -1, still concave down. So I'm going to increase. I'm going to erase a little bit of this because I want to go a little bit steeper when I'm drawing it, because we see that we have to also hit this the y-intercept at some point. So steeper, concave down. This should be looking a bit more continuous than it is. Imagine this is connected. And then at -1, we see we start to decrease and we're still concave down. So I'm going to continue concave down. And I see that I have to decrease continuously and hit our y-intercept. From here, though, we change to concave up. and we're still decreasing. So while this looks like concave down, I'm going to make a point to decrease concave up. And you can see a very clear shift in concavity here. And then from here, we're increasing concave up forever. So I'm just going to increase concave up. Oh, I missed my intercept. See, this is why we go ahead and check. So this has to touch our intercept. So I'm going to decrease to our intercept. So let's see, we're decreasing concave up until here. So we have to hit this, but then we continue up like this. So it's always good to check our work because we need to make sure that we hit all of our x-intercepts, our y-intercepts, and we're following all of the rules on the bottom of the graph. All right, let's go ahead and do one more example. I know this video is kind of long, so the next example is going to be a little bit more abridged, which means that I'm giving you all of the information. So this is actually from either last lecture, last lecture. We already found all of this information. So this isn't like I'm just giving it to you. We already found this. You watched the video. So we're just going to be sketching this. So we have all of this information right here. Let's go ahead and sketch the graph. All right, so I'm going to go ahead and get my axes going, and I'm going to write what's happening at the bottom here. Let's see, 0 to 6, intercept is 0, 0. So here is my y-intercept. This is also my x-intercept. And then at 6, 1, 2, 3, 4, 5, 6, this is also going to be an x-intercept. I see that I increase from negative infinity to 0. So I increase here. And then I also increase from 4 to infinity. So here's 4, which is about here. And I increase from 4 to infinity. It says I decrease from 0 to 4, which is exactly what I have left. I decrease here. It says I'm concave up from 2 to infinity. So here's 2, 2, going forever. This is concave up. And then from negative infinity to 2, I'm concave down. So from here, forever, I'm concave down. All right, now we've covered every single bit of information we're given, and we can actually sketch the graph. We know that we have to go through this point right here. It's both the x-intercept and the y-intercept. We know that we're increasing concave down. So again, I can't start up here increasing concave down because then I never hit this point. So I know I have to start like this, increasing concave down, hit that point, I'll draw a little arrow. And then I notice that my first change in anything is going to happen at 2. So I'm going to continue to increase concave down until I hit 2. Oh, I apologize. That was not my first change. You notice that my first change was actually at 0. So that's why, again, I draw everything at the bottom because then we can double check our work too. So we notice we're decreasing now until 2, concave down. So decreasing concave down looks like that. Starting at 2, we are going to be still decreasing, but concave up. And then the next change is right here at 4. So decreasing concave up will look like this. And then we're going to be increasing concave up forever. And we know we have to hit this point. So we go up, hit this point, go up forever. And this is what our function is going to look like. So even though I may miss a step at some point, as you can see, there's a lot going on here, and even I miss some steps. So make sure when you're doing questions like this, there is a question on the written assignment on this type of a question. Make sure that you're really paying attention to every little detail because it's really easy to just miss a tiny little something and then your function gets a little bit messed up. All right. As always, if you have any questions, let me know. Sorry this video was so long again, but we had a lot of important topics in this. So if you have any questions, let me know. And congratulations for making it through 4 weeks so far.